Okay, now, so here's an example. Take a derivative of x cubed minus 10x squared plus 40x. That's going to be 3x squared. You put the 3 in front, and you reduce the power of x by 1. And here it's going to be minus 20. That's, you take the 2 and you multiply it by minus 10. So that's minus 20x to the power of 1. And that's just going to be plus 40. Okay, so you've got 3x squared minus 20x plus 40. Okay. Okay, so let's talk a little bit about interpretation. Here you have a polynomial to order 3. Okay. So Kathy asked me a question in the break about how I ended up with a weird looking cost function based on some cost function that I had put up. Okay? And so I just want you to get a sense of the rules that I was using, because it's a sort of rules of thumb, but you'll find them useful. Okay? Now, I'm only speaking about it relatively quickly here, but in the website resources that I gave you last time, in particular the SEPA math resources, where there are detailed notes on all of this, you'll find a section on different kinds of nonlinear functions, and one of those will be polynomials of order 2, order 3, and so on. And there you'll see some graphs, so you can follow up further on it. But in particular, a polynomial of order 1 is a linear function. Okay, that, for example, 2x plus 1. That may not be quite right. In fact, this is probably 2x minus 1, right? Okay, that's a polynomial of order 1. A polynomial of order 2 might look like this. Okay, what's the difference between the two expressions? The highest power of x here is 2. The highest power of x here is 1. Okay? Okay. Now, a polynomial of order 3, which is what my cost function looked like, will look like this. And so that'll be something like okay. Yes. In my definition of convexity and concavity, I actually didn't use the full-blown mathematical definition in order to simplify things. In particular, you call a function convex or concave not over its entire domain, but just for an interval. So if it is monotonically increasing in an interval, then it's convex in that interval. So along this part, along all of this, it's convex, and along here it's concave. Okay? So you know, for more complicated functions, they'll be concave and convex for different intervals. Okay, so that's a very good question. Okay. Okay, so we wanted to interpret this example. We had here a polynomial to order 3. It'll look something like that. And the nature of our differentiation, remember that when I take this derivative, I end up with something that is an expression that gives me a polynomial to order 2. Okay? So that means that if I start out with a polynomial like that and I take its derivative, then the derivative will look something like that. Okay? Simplify. And the derivative of this will be a straight line, and so on. So that's why I was saying earlier that, you know, many functions that we could construct just randomly, often we would construct them this way as polynomials of higher degree. You simply take derivatives to get to a straight line. Yeah. You know, and that's and many complex scientific models are built that way. They're simply you know, there are you know, because usually when we build these models, we build them from simple building blocks. For example, we think that there might be some linear relationship between, you know, we generally, so if you think about, one of the things that I'm interested in is weather derivatives. And, sorry, actually, that's not a good example, because I was thinking that weather derivatives, there are different kinds of derivatives. I was thinking of financial derivatives, not calculus. So let's say you want to model something like precipitation. Precipitation is not generally a linear function of anything, but different pieces of it, different building blocks might be linear functions. You know, when you build a climate model, you might think that whether or not the monsoon will come before a certain high pressure system develops over the Indian Ocean is a linear function. And so that piece will be linear, but that plus some other linear piece put together, interacted, might not be linear. And when you build a model, it might end up looking approximately like this. But then when you start to take derivatives on different dimensions, you'll end up with linearity, because you'll have ended up, even if you don't know exactly how the modeler started their thought process, just by taking derivatives, you'll get to an approximate relationship. Okay, so that's, yes. Yes, through the mathematical calculation. Yeah, it would be, usually these will be multivariate functions. So you wouldn't really even have a graph. I mean, it would be a multidimensional graph. You'd have to take a single section through, and then you'd get a graph. And it would be, you wouldn't do it that way, basically, right? Okay. Okay, so now, we get a somewhat simpler, you know, a polynomial of lower order. And and then this functional relationship simply tells you the slope of the original function for whatever values of x. So this was Davida's question earlier about, you know, I didn't get why the derivative, what happens if I plug the value of 5 back into the derivative? Well, it simply gives me the slope of the original equation. So if I plug the value of 3 into this equation, it'll give me the slope of that equation. Okay? Okay. Okay, and you could actually just do that numerically. So the rule that you saw that that you're used to is the power rule, but not the general power rule. Okay, so if you take something like 5x cubed, its derivative is 15x squared. You're taking 3, multiplying it by 5, times x to the power less than 3, 1 less than 3, okay? That's when x is multiplied by a constant multiple, 5. But suppose that x is multiplied not by a constant, but by another function. Okay? Suppose that instead of 5x cubed, I had let's say x, take the square root of x times x cubed. Okay, there are multiple ways you could do this, but one useful rule to keep in mind is the general power rule, which is if you have a function that says, if you have a function on the inside and you raise that whole function to the power n, then the derivative, you put the n in front of the overall function, you keep that overall functional form, you take n minus 1, then you take the derivative of the inside function and you multiply it by itself. Okay? And you could apply that rule. If I just had 5 here, you could still apply that rule. You could think of 5 as a function. What's the derivative of the function 5? 0, okay? And so you could just think of that dropping away. But so let's suppose that we do an example where we've got g of x, let's say g of x is equal to the square root of x. Okay? And we've got the larger function being raised to the power 3. So I have to find the derivative of the function okay, so the one way you could do it, if you remember your laws of exponents, is how do you express this? X to the half, right? So this would be x to the half. So if you take the brackets out, it would be half times 3, so that would be 3 halves. So it's really x to the 3 halves. Then you take the 3 halves, put it in front, minus 3 halves minus 1, and so on. You could do it that way. Or you could use this approach, which says that you're going to take the n, that's the 3, times the inside function, and then 3 minus 1, okay, times the derivative of the inside function. And here, what's the derivative of the inside function? Well, that's minus half x to the minus 3 halves, right? because the inside function is really x to the half. So that becomes, oh, sorry, that becomes half x to the minus half. Sorry. Good catch.
So the derivative of x to the half is half x to the minus 1/2.
That's right. Okay, so this is one step. That's how I get this. Multiplied by this thing. That's just a 2. And this is going to boil down. This is just x to the half. So again, you could do half times 2. That would just be 1. And you couldn't boil this down, because this is still going to be minus a half. So you'll have an x here and an x to the minus half. So it'll be something like x over the square root of x times the coefficient. Okay? This stuff, clearly some of you are familiar with it, others it's going to be new for you. You're not really going to use it in the economics classes. You may use it a little bit in some of the science classes, but you're not going to use it in the way that involves you having to memorize any of it. In other words, you have to know that these rules exist, and you have to know that if you're faced with a problem where you have to take a derivative and it has a certain amount of complexity, then you'll want to use these rules. So I'm going to just go ahead quickly through some of them so that we can get to the multivariate part, which is actually conceptually a little bit more complicated, but requires that you know this. Okay, and if you like, you can do the examples that I've given you on how to employ this. So here is actually a slightly easier version where the inside function is 2x plus 3 as opposed to x cubed. Okay, and you use the power rule. You work out the outside derivative, and you work out the inside derivative, and you multiply that times that to get you the final answer. Okay. You've seen the constant multiple rule. You know the sum rule. Okay, the product rule is something you should see or know about, because you'll see this a lot. Often you have a function that's the product of two functions. Well, you could multiply out the two functions and then take derivatives term by term. But sometimes, as you know, when you multiply out a function, or when you multiply out a product with many terms, it'll look significantly more complicated than when it is kept in factored form. In fact, very often you spend your time simplifying into factored form, right? So you don't want to have to multiply that out before you take a derivative. That's why the product rule is useful. The derivative of that product function, f prime, is the derivative of g times the function h plus the function g times the derivative h prime. Okay, and this, if you took calculus in college or high school, this is probably one of the rules that you still remember. Okay, and so this allows you to compute the derivative of g, compute the derivative of h, substitute g and h, and then you have a much more simplified expression, and then you compute what f prime is. Okay? Yeah, let's do that example. Again, if I'm just glossing over things, stop me and say, let's just do that example, right? Okay, so you've got f prime x is really equal to, in this case, the product of two functions. This is g of x, and this is h of x. Okay, so I simply substitute my rule. I know that that is g times h prime plus h times g prime. Okay, well, g is just that, x minus 3. H prime, what's h prime? 4x. And h is 2x squared minus 1. And what's g prime? 1, right? And I could simplify this out and so that's going to be 4x squared minus 12x plus 2x squared minus 1. Okay, this and that will give you 6x squared minus 12x. And that's what hopefully I have up there. Okay? Okay, so what I did is I compiled a whole bunch of useful rules and I put them on a couple of slides for you. We don't need to go through these, but they are sometimes useful when doing problem sets. Okay? Derivative of a constant, derivative of a linear function, derivative of polynomial functions. Something that's useful to keep in mind, the derivative of the function e to the x is what? Is e to the x. Okay, so this function is actually constructed so that its slope is itself. Okay, so the slope of this function e to the x is always equal to its value.
Where is that applicable?
Sorry?
Could you give us an example of how where we define that?
Well, it's a very useful way of showing exponential. Sorry, this is the inverse of that function. Sorry. Okay, so it has biological applications. In particular, suppose that the the growth of some proportion of a species in the population is dependent on the size of that proportion in the population. So you would imagine a scenario where if you have a species, the bigger a portion of the globe it takes up, the faster it grows.